Good afternoon. We're going to get started. I'm Dr. Kay Stefanik, Assistant Director of the Iowa Nutrient Research Center. I want to welcome you all to our spring seminar series, Focus on the Future. This is going to be just like our fall seminar series, where we usually have two presenters who are either current or recent graduate students that have done work on INRC funded projects. They will be presenting on not just their research, but also their experiences as early career researchers. And I just have a few housekeeping items before we get started. This seminar will be recorded and posted online for viewing later, and it will be accessible through the INRC website. And then second, we're going to have a Q&A section at the end. So if you're in the room, just raise your hand. If you're online, you can either type your question into the chat box and I can read those off, or you can wait till the Q&A, unmute yourself, and ask your question directly. Okay, so for today's seminar, we originally had two speakers scheduled. Unfortunately, one of them had a family emergency, so she is unable to present today. So we will have Dr. Mitch Baum speaking. He extended his presentation by just a little bit, but you'll probably get to go home a little early today. As I said, our speaker is Dr. Baum. He completed his PhD at Iowa State University and worked with Dr. Sartorius Arcantoulis, and he is currently a postdoc working with Dr. Mike Castellano in the Department of Agronomy. And he's going to be speaking on the effects of genetic, environment, and management factors on economic optimum N rate.
Great, thank you. All right, took most of my first slide for me. Thank you very much. So currently, after I moved into this postdoc position, I've been working as a lead kind of data analyst for the Iowa Nitrogen Initiative. And the main goal of what we want to do with the Iowa Nitrogen Initiative is that it's a public-private partnership between Iowa farmers and us here at the university to advance nitrogen science in terms of management for productivity, profitability, and environmental performance. That sounds kind of daunting, but what we really want to do is reduce the uncertainty around nitrogen decisions when farmers are making them, and such as what rate. It rained a lot this spring. Should I apply more nitrogen? How many times should I split my nitrogen amount when I need to apply it? And we want to reduce this uncertainty so that they can hopefully apply optimal nitrogen rates which best fit their system, and in turn has productivity and environmental benefits. This is done through hundreds of on-farm trials spread across the state of Iowa. Each trial is relatively small, only a handful of acres with roughly 5 reps and 3 to 5 N rates apiece, but they're selected based off farmer knowledge and the field agronomist with PCS that helps set up the trials, and they're typically done in stable areas of the field, like here in this top left corner, where it's a high yielding stable region, as well as less stable regions in lower areas of the field, which could have differing requirements for nitrogen rates. Now, typically, I want to define what an optimum N rate is first. In simplest sense, it is the nitrogen rate where there is no further increase in yield to applying more nitrogen. And we do this, we're able to estimate this optimum rate by fitting a host of statistical curves through to yield responses to nitrogen. And the best fit curve will tell us what the optimum N rate is. However, farmers don't think in just terms of yield and nitrogen. They also have to worry a lot about economics. So we try to think about the economic optimum nitrogen rate, or the nitrogen rate that maximizes a farmer's return on investment. Here, and for the rest of this presentation, I'll be focusing on the economic optimum nitrogen rate. Sometimes I'll say optimum N rate or just opt rate. I'll do my best to say economic optimum N rate, but this is what I'm talking about. And this is determined by using the price ratio of fertilizer and yield. While both are relatively fluid within the market, the ratio between the two is relatively constant across time in metric units at about 5.6 dollars per kilogram nitrogen to kilogram yield. Now, that's economic and productivity reasons, but what about environmental? So another side project with the INRC that I was able to work on showed that there were relatively little nitrogen losses, specifically nitrate leaching, when nitrogen is applied less than the optimum N rate. It's really, the problem is when we exceed planting or applying at the optimum N rate, that nitrogen losses, specifically N2O gas and nitrate leaching, really starts to leave our system. The challenge to that is it's very hard to apply the right optimum nitrogen rate because it's changed and it's very variable across space, which we can see here. Within one of these box plots, there is 7 or 14 different field locations within a single year. And we can see that the optimum N rate is changing, in this case, in the furthest one here in 2000, from about 50 to 240 within a single year. Now, granted, why? So within each of these, there's obviously different soil types, different management, and of course, different weather across these sites. Another important thing to note is that the economic optimum nitrogen rate is changing across time. Typically here, I'd like to ask the audience why you think it is, but given that there's so few people in the room, I'll just mention that we think it's largely due to increasing yields, right? So as yields increase, the demand for nitrogen increases as well, but that has some other effects like increased residue amount. Increasing residue amount can really limit the amount of mineralization in the spring by keeping the soils just a little bit wetter and a little bit colder, a little bit longer, which can reduce nitrogen mineralization. It is also getting wetter. Over the last 30 years or so, our springs across Iowa have been getting a little bit wetter, which is increasing nitrogen leaching, further increasing the demand for nitrogen fertilizer to reach the economic optimum nitrogen rate. To further explain this, and this is really the heart of my NRC project, was to calibrate optimum to these yield response to nitrogen studies in order to determine, well, one, if we could predict it, but two, maybe we could help understand a little bit of the uncertainty across space and time with them. And now optimum is a biophysical process-based model, which takes into account soil, weather, and management data, and it analyzes what it thinks the crop will grow on a daily time step to help predict how the crop is growing across the growing season, but as well as nutrient cycling, such as nitrogen and water throughout a given system. To calibrate this, I took in weather data from the Iowa Mesonet and NASA Power, soil data from what we knew about these experimental locations, as well as GxExM to kind of provide a base in which we tweaked ever so slightly within the range to best get a yield response to nitrogen. And then, of course, any known management we have from the systems, particularly planting date, planting density, tillage, crop rotation, harvest date, and anything that we could find useful to help define how the crops were growing within the system. And our key outputs were one, of course, yield, which we then used to estimate the optimum nitrogen rate, and nitrogen losses in terms of leaching and N2O. Now, in terms of yield, how did we do? We did really, really well, right? And this is no surprise. Across the literature, optimum has been shown time and time again to be able to simulate yield on a fairly consistent basis. So here, this 1-to-1 plot of measured yield and simulated yield is from all 14 locations, all 20 years, and all different nitrogen rates. So we were simulating yield really well. How did that translate to the economic optimum N rate? Well, not as good. So you can see there's a very clear underestimation of the economic optimum N rate from the model as compared to what we see in reality. And to pick on this one point here in the middle, just to show how the yields were matching up, where the red line is APSIM simulated yields and the black lines are measured yield points, we can see that the model itself is doing really well at simulating the yield response to nitrogen. However, if you were to look at the optimum N rates between the two, it's a difference of 80 pounds, which led to a couple of questions of why this is happening. The first was we wanted to run a sensitivity analysis on different nitrogen rates by removing them completely and refitting the curve that's used to estimate the economic optimum nitrogen rate. Because we knew that the model was simulating well yields at the high nitrogen rate, but we can see that here by having a lower root mean square error between the predicted and simulated data than it was at lower nitrogen rates. Luckily, when you removed the lower nitrogen rates from this equation but kept everything else constant, the effect on the optimum N rate itself was relatively small, with a mean change of only 7 kilograms nitrogen per hectare. The important yield point to get with the model is simulating the high nitrogen rates, because reduction or removal of that can change the optimum N rate by plus minus 50 pounds on average. Fortunately, as mentioned before, that the higher nitrogen rates are what we were simulating really well. And the reason why we can simulate these high nitrogen rates really well is that the model looks at potential yield throughout the entire year based off weather conditions and management, and then it reduces daily limitations. So if there's a nitrogen stress or a water stress, it'll reduce the growth that day. And at very high nitrogen rates, we don't have to deal or worry about nitrogen stress within the model. So therefore, the main source of error is really water stress in this case, assuming we know everything about the management. And at 0 N, it has to deal with the interactions between water stress and nitrogen stress to try to predict yields, which is much harder to do. Here is just another 1-to-1 plot showing that essentially the same thing, that the higher nitrogen rates are much better simulated than the 0 N rates, where the left side is the continuous corn and the left side is corn following soybean crop rotation. The second reason we wanted to explore was, well, maybe the problem isn't with the model. Maybe the problem's us. Maybe there's a human error. And in terms of human error, I mean selection of the best fit statistical model, because the selection of the best fit model can have a big impact on the optimum rate itself. And we can see a big mismatch between the simulated and observed. So the observed best fit model tended to almost always reflect a quadratic or plateau function, or better put, there was kind of a diminishing returns to nitrogen until it reached the optimum point and then it plateaued. Whereas APSM tended to prefer a linear plateau, which means yield just kept increasing and increasing until a certain point, and then it reached the plateau wherever nitrogen was not limited. And the selection of the two can have a big impact on the optimum rate. On average, if you were to fit both the quadratic plateau and the linear plateau through the same set of data, the optimum N rate or uncertainty caused by the model selection is 50 pounds of nitrogen, which has, big implications on when a farmer's trying to make decisions. But regardless of model selection, it has very low effect on yield. So the optimum yields are the same per model, but what really changes is the N rate itself. So we redid the analysis, but this time we took out the effect of our error. We only selected a quadratic plateau through the APSM data. And what we found was here is the site averages of the observed EONR in the black line, only using the quadratic plateau or the model that best fits the data, the orange line, and the variable model selection in the blue line. We can see that pairing what we see in real life with how we want to analyze APSM greatly improved our prediction of the optimum between the optimum N rate and the simulated optimum rate. Now, this work the EONR. However, this was all just extra stuff. Now we can get into what I actually came here to talk about today, and that is the effects of genetics management in the environment on the economic optimum N rate. This actually was kind of an accident that wound up being a third chapter of my PhD. So during the calibration phase of APSM, Satirius and I were trying to run an experiment to see best ways to calibrate the model and see which factors were really pushing and pulling the optimum N rate in the direction we wanted it to go. So we ran a local sensitivity analysis. That is, I changed one thing at a time. For instance, in case of planting date, I added a newer May 1st to May 20th, and we saw how that affected the yield response to nitrogen. Or I applied everything at planting versus split between planting and at V6, or the 6th leaf stage. And we did this for 3 of the well-calibrated locations from the previous 14 studies. We chose these 3 because we wanted to get a temperature gradient from north to south, from as far north in Iowa as we could get to as far south in Illinois, but also east-west to get kind of a precipitation gradient. From the furthest west in Iowa, we could get the driest location on average to one of the wetter locations in Dixon Springs. And then, of course, we had to include Ames right here in the middle. The specific factors we looked at, I won't go into a ton of detail here, but here they are on the slide. These are the main management factors we think a farmer can play with. genetic factors, which we know a farmer can select, such as crop relative maturity, CRM, crop radiation use efficiency, which can't be selected for, but is something well documented, and we know that is changing over time and specifically across hybrids, and then critical grain end concentration. In terms of environmental factors, we created what's called a baseline, and that's running the model for 30 consecutive years with an annual reset right after harvest of the first year to avoid any residual impact of what we had changed in the sensitivity analysis. And then we used everything based off this baseline of weather. And then in terms of other soil factors we changed soil organic carbon plus minus 15%, residual N from essentially nothing in the fall to 90 pounds. And then we played with the water table depth. It should be noted here that all these simulations are run without tile as a baseline, and that was one of the scenarios we added in later. The scenario analysis, sensitivity analysis itself, can be calculated kind of as a percent change, where we took the max change minus the min change divided by the max, and that'll tell us how sensitive it was to changing that parameter. In terms of, I'll pick on planting date again, how did the optimum N rate change at an early planting date versus a late planting date? And we can see this, use that to determine the sensitivity of the optimum N rate, the yield at the optimum N rate, and the blue arrows stand fit here, but also how that would impact the yield at zero, or really, soil conditions and mineralization of that system. And it can be interpreted as a value of 1 as this parameter or this scenario is completely sensitive, or the optimum N rate will always change based off of this change to management or G by E by M effect, or 0, it's completely non-sensitive. It has no effect at all. To get a sense of how things are changing, first we look at RUE, which is really increasing yields at the high N rates. And this is driving up not only the optimum N rate itself, but yield. And this is important because nitrogen use efficiency has been shown to be increasing fairly steadily over time from the 80s to now. Then moving on to critical grain end concentration. This doesn't really have an impact on yield at 0 or yield at the optimum N rate, but it really does impact the nitrogen use efficiency of the crop, where here a lower critical grain end concentration really is, doing more with less nitrogen. So the curve is actually a little bit higher and steeper, and that's causing the plateau earlier and vice versa. Crop relative maturity was relatively non-sensitive. However, we didn't test a very variable range. I only went plus minus 6 days versus the baseline. Where here, though, the high CRM actually penalized yields ever so slightly and reduced the optimum N rate, likely due to those years, likely due to the cases when the crop wasn't able to reach physiological maturity or reach its full potential. Soil residual nitrogen really didn't impact yields at the high N rates, but it did have a big impact on yields at low nitrogen rates, showing that when there's a lot of nitrogen in the soil, you don't need to apply as much to reach the optimum yields, and therefore you can apply a little bit less. The same with soil organic carbon, SOC here. Water table depth was surprisingly non-sensitive to us. We really hypothesized that a shallower water table would restrict roots and therefore yield and uptake within the model, but that happened to not be the case with these simulations. I won't go through all these, but I'll stop here on tillage, which is something that farmers consider every single year, and that's the difference of full till and no tillage, where full tillage or complete essential moldboard plowing did increase yields at 0 and reduced the optimum N rate some, likely due to increased mineralization and vice versa for the no-till environments. But when we try to compare all these things together, what was the real main driver of the sensitivity of the EONR? And that wound up being weather variability, something we can't really control for. Followed in part by radiation use efficiency. This has to do with the correspondence of yield within the model and the optimum N rate, and then residual N itself. How much soil nitrogen is being supplied by the soil. Just a refresher that radiation use efficiency really is pulling up not only the optimum yields, but the optimum rate when it is increased, and that the residual N can really pull the EONR back when there's a lot of soil nitrogen. In terms of, oh, you really can't. So this is supposed to be the sensitivity of the yield at 0. And here it's completely all driven by annual weather. So things that are really impacting the yield at 0 N is really the amount of rain and the amount of nitrogen in the soil. And of course, we can impact that with tillage, whereas a lot of tillage causes soil to dry up a little bit quicker and can lead to greater amounts of mineralization and vice versa. And planting date. Planting date is seemingly having a significant impact on that, likely due to later planting dates are being planted when it is warmer and there's greater mineralization occurring in the soil. And then here is the sensitivity at the highest part. Once again, weather is dominating the variability here, but opposed to that is RUE. Planting date is also a big one here. At the high end, we don't think that this is caused by changes in mineralization. We believe this is actually due to a later planting date actually not being able to reach its full potential. What we can see here on the bottom graph is that the earlier planting date, which wound up being April 15th, was pretty much the same as our baseline planting date of May 1st. And that's because, given the relative maturity selected, the plant was able to reach its full potential across both dates. It wasn't until we pushed the planting date to a region where it was no longer able to reach its full potential that we saw a little bit of a yield reduction and a pretty significant drop in the optimum N rate, because not only did it reduce yields at the high end, it increased yields at the low end, creating a pretty strong pull towards lower optimal N rates. Well, so one of the main limitations of this study is that in the real world, all these things are interacting with each other. And when you change only one thing at a time, that's really good for understanding that individual effect, but it may not be explaining the entire story. So we wanted to look at a couple things stacked together. Here specifically, earlier planting date and improved genetics. We specifically chose these three because this is what we think is going to happen as we move forward into the future. We've seen higher planting dates across time, or higher plant populations across time. Planting date really isn't changing a lot. There's some evidence that it changes 1/10 of a day per year. So 10 years from now, maybe 1 day earlier on average. So take that what you will. And then of course, improved genetics, which we know is constantly being improved through the private sector. Here, I say improved genetics, I really mean it has a little higher RUE, radiation use efficiency, a little bit lower grain nitrogen concentration, and I also increased the CRM a couple days because it's going to be getting a little hotter. Adding the higher plant population with the improved genetics, which is what we really think is going to be happening, saw both advances in yield and coincidentally the optimum N rate in order to sustain the yield, planting date plus improved genetics was more or less the same, really showing the increase here that of the genetics has on the optimum N rate. And then combination of all three is just a little bit higher than all of them. What I think here is interesting though, is the combination of all three has the lowest variability of yield at the highest N rate, but it's coupled with the highest variability of the economic. It's coupled with the highest variability of the N rate. To push this even farther, we added a climate change scenario, and not in the typical sense where we tried to predict what the weather is going to be in the future. What we wound up doing was this was actually wound up being published by Dr. Elvis Ali, another alumni from Dr. Arcantulis's lab, where he used a bias correction factor per month, which was leveraged against 15 known carbon representative pathways for what we think the future weather is going to be. The reason why he did that was because when looking at the RCP pathways, one thing we noticed amongst all of them was they didn't have the same amount of weather variability we've seen the last 30 years. So we wanted to maintain that, yes, there may be changes in precipitation and temperature, but we didn't want to lose our annual weather variability. So therefore, we added those bias correction factors to our known weather. And what we can see is if we keep everything business as usual, or a planting date on May 1st, plant density of 8.6 plants per meter squared, everything that we've done today, the optimum N rates decreased by 25%, and that is coupled with a decrease of about 15 to 20% in yields. It wasn't, so clearly that's not good. We want to at least be maintaining yields or even advancing them into the future. So we added, once again, our three stacked things: higher plant density, earlier planting, and improved genetics, to see if that could help mitigate these effects of climate change on the model, or on the yield and economic optimum N rate. And what we found was, alone, no single factor could reach today's yields or economic optimum N rates. It wasn't until we started adding factors together that things actually started to improve, and we could actually mitigate some of these negative effects of climate change on the model. Actually adding all three of them together was the best way forward. So increasing plant population 20% from where it is today, an earlier planting date by 2 weeks, and of course improved genetics. It's really a coupling of all three that allows us to get back to baseline conditions given future climate change. To wrap this up, I think I did exceed my extra 15-minute time frame. yes, the EONR is highly variable to all genetic management and environmental factors, which showcases why we need to place better effort on the ability to predict it. But we have to be able to look at all factors of the system, because all things have a hand on what the optimum nitrogen rate could be. Weather was the dominant factor, but controlling 41% of the sensitivity, but that means we can manipulate things, the other 60%, like management and genetics within our system, to help reduce the sensitivity of the optimum N rate, or at least better understand or change it to the way we want. And in order to mitigate potential impacts of climate change on the EONR, it's going to take an effort of everything, management, genetics, and genetics to alleviate the negative impacts of climate change. And with that, that was my last slide. I'd like to thank the INRC for in part funding all aspects of this project, my PhD advisors, Thierry Sarkantoulis, and all the members of his lab that helped me through it. And now I'll take any questions.
Are there any questions in the room?
It's one online. Okay. You showed N rate in corn soybean rotation at 3.44 kg per hectare per year, I guess increasing it that much.
Yep.
And continuous corn at 2.58. Historically, we've said soybean got about a 50 pound per acre rotation effect. Your slopes would suggest this is changing, but about 15 pounds per acre over the last 20 years. Thoughts on why this rotation effect might be?
Yep. No, that's a really good question. And the reason we've seen is that the yield response itself, or the optimum yield at the optimum N rate minus the yield at zero, is increasing faster than it is in continuous corn systems. So what that really means is, well, maybe it's in here. Perfect. Actually, it is in here. So what that means is the shape of the curve is actually becoming steeper. So historically, one of the things we see why there's a difference between the two, not only does it yield slightly better with higher yields at zero, but it's flatter. So the difference between the optimum N rate and the economic N rate is farther than it would be in a continuous corn system. And with the maize following soybeans, as that becomes steeper, that is increasing slightly faster as well. Yeah.
When you looked at the weather variability, do you look at kind of how much deficit water stress or drought stress there was on the crop?
In the future climate scenarios?
Or even the future or current? I'm just thinking, if you looked at the potential for irrigation, what that might do to the future crop.
Well, here in water management, irrigation is this greenish tan line, and this is based off soil water deficit.
Okay.
And now this isn't under future climate scenarios, but hopefully it gets the same point across. And we can see that it actually does benefit yields, right? So obviously, if we're alleviating water stress, we can yield just a little bit higher on average. And this had just a slight increase on the optimum N rate. Now, I suspect a follow-up question would be, what if you had tile drainage and irrigation? And that's unfortunately something I didn't look at here, but it is something of real interest to me, because tile drainage, while it wasn't very sensitive, it did increase yields just a little bit, and it did decrease the optimum end rate. So it really increased the efficiency of our system by including tile drainage.
So if I look at that, the black line would be no tile drainage.
Yep.
And then whatever.
Yeah,
Whatever
tan,
that
sure,
color is,
would be with tile drainage, and that's set up the standard like 1 meter down, I believe, 18 feet across. What is that in meters?
Yeah.
Yeah.
15 feet, 16 feet, yeah.
60. Oh,
guess
sorry.
I'm-
Yes, no, that's right. Sorry, I had two different tile drainage simulations.
I should have asked you about this before, because, you know, I was on your committee about this, because I would expect tile drainage to have a bigger impact on yield than this show.
Yes, that's a great question, and we think once again is because we kept everything else held constant. You know, we know the benefit of tile drainage is it's drier a little sooner. You can plant a little earlier, and here, even if the soil was drier and the farmer could have gone, we still planted, you know, the same date and kept everything else constant.
Because I still think with the drainage, you might get more excess water stress even during the season. That might negatively impact the crop.
Interesting. And in the real life, that could be, you know, a function of models that we're still needing to.
And is this
fix.
for one specific site?
No, this is an average across all 3 sites. So,
Sorry, could you remind me what the 3 sites were, where they were at?
yeah, of course. Oh, you're there. So we have one in Sutherland, O'Brien County, here, obviously, and then Southern Illinois.
Mitch, on your second last, or the last slide of the conclusion on climate change mitigation. So yeah, the next one.
No, sorry, they look the same.
So that's so your combination there. That's telling me genetics plays a very important role.
Right.
That's probably the most important role. Am I reading that right? Those combinations that you're showing here.
With the combinations that we selected, yes, it is. And we assumed that the RUE would increase to a certain point. That's the main driver of the yield in this case, because that's what we've been seeing in the past. If that were to level off in the future, then we wouldn't see this exact same response.
So you're seeing us progressing.
Yep.
Gotcha. Big role of genetics. Huh?
Yep. Which is good. There's a lot of money being poured into them. So
So I thought it was kind of interesting that you mentioned this came off as kind of a side project from something you weren't really thinking about initially. And I feel like that's probably something that a number of grad students have experienced. Could you maybe talk a little bit about kind of how you started that process of deciding to look at this?
Yeah, so the whole point of my PhD was to be able to predict the optimum nitrogen rate, and we really weren't sure how we were going to do that. We knew we were going to use APSIM, and we were going to use this vast network of yield response to end trials. But once we really got into it, we just kept asking questions. You know, it's why is the model behaving the way that it is? So to do that, we started changing one factor at a time, which is something that anyone that's calibrated a model will do. Is they'll change something, and they'll run it, and they'll see how it changed. And they're like, oh, that was good. We'll write that down and come back to it later. And then we did that enough times where we started to think, you know, this is kind of representing what we see in the literature, and in reality, we might have something here. So I expanded it to far more G by E by M effects, we added in the climate change component. And we hope it'll get published relatively soon. But yeah, I guess the whole process was just continually thinking and not just being set in stone about what we wanted. We knew we wanted to help predict the optimum N rate, but we couldn't do it with how we were currently thinking. So we updated our approach and we wound up tacking this on top of it.
Was this an developed from the 5x5x5, or was that separate?
The 5x5x5 is separate, but it's very similar. It's a
Right.
very similar, experiment. That's actually being worked on currently, being put into AppSim. I don't know if you've seen those results yet.
What's the 5x5x5 experiment?
That's a great question. So it stands for 5 nitrogen rates, 5 hybrids, and 5 plant densities. So it's a very big kind of interactive study on, how those different factors affect the economic optimum N rate. And actually it was just published a month or two ago in Agronomy Journal. I'd be happy to share that paper with everybody about how, so what that paper showed was, maybe I'm getting past your question, was a response surface of various, how the economic optimum N rate changed at different plant densities and how we could adjust the two to kind of still maximize yield. So for instance, we could still obtain 99% yield with increasing plant density and N rate versus, a little bit lower N rate and a little bit lower plant density, or vice versa. There's a different combinations. That one's a cool study. Yeah.
Out of this then is a takeaway in terms of water quality.
Terms of water quality. So the main thing is predicting the optimum N rate can reduce these nitrogen losses we see. So if we're able to predict the optimum N rate, improving water quality is going to be a very beneficial side aspect of that. And
Because you're
Yep.
reducing risk. Right?
Yep.
So, Mitch, with this now, this information, what would be the next step with that?
the next step with AppSim is going to be take what I did was a local sensitivity analysis to a global sensitivity analysis where all these factors are interacting with each other. And that's luckily for me a different PhD student. But that is going to be the next step with this AppSim project. And yeah, no, I'd be very interested to see how all these things are interacting because we know that they are.
All right, so it doesn't look like we have any more questions online, and we are at about 4 o'clock. So thank you again so much for your presentation. This will be posted online, so if you want to watch it later or share it with your friends, so thank you.
Oh, great. Oh, thank you guys. Glad I was able to kickstart this semester.
That was great.
Yeah.